Okay, this is then the beginning of working various problems involving the moist air. This first problem out of your textbook is example 1210, and what it involves is the heating of a moist air stream in a duct. And this particular case, because it's heating, there is no condensation of moisture and there is no addition of moisture. And so this particular problem then at station 1, we have conditions associated with the moist air mixture. We see that the dry bulb temperature is 10 degrees Celsius. The humidity, the relative humidity is 80%, and the volume flow rate of the mixture itself is 150 cubic meters per minute. And so there is heating occurring into the control volume, and what happens is the dry bulb temperature raises to 30 degrees. So now if we were wanting to look at this particular process dealing with the moisture in the mixture, we can look at a TV diagram for the water vapor, and we could identify the thermodynamic state of the vapor at the initial condition. And as we see here, it's very close to the dome, it's very close to the saturated condition, and it's at 10 degrees Celsius. And so if we follow a constant temperature line, we would then be able to determine at that amount of vapor corresponding to 80% relative humidity, which we could obtain from a psych chart, we are at this particular location. Okay, during this process, heat is added, no additional moisture is added, and so the process going to state 2 is a constant pressure, constant partial pressure process. There is no additional moisture brought in, and so the partial pressure of the moisture stays the same. And so that would be running up a constant pressure line in the water TV diagram until we run into temperature 2. And so our final condition would be this condition right here. And so from our psych chart, we should be able to obtain the enthalpy value for this point. From our psych chart, we should be able to find the enthalpy value for this point. And the difference between the enthalpy is then related to the heat transfer. The only thing that we have to determine is from this information here, what is or how much is the mass flow of dry air through the system, which stays constant. And so that would be the m dot of the dry air. And so I recommend that you take a look at this particular example problem. Okay, typically what we use psychometrics on is air conditioning. And when I say air conditioning, there are a couple of things that come to mind. First of all, a increasing or decreasing in the temperature associated with the mixture. If it's winter time, you might want to increase the dry bulb temperature. If it's summertime, you may want to decrease the dry bulb temperature. But in both scenarios, you might also want to add or subtract moisture, because of moisture in the air gives rise to a more comfortable condition sometimes, or lack of moisture. And so in this particular scenario, what we see happening is that we bring in moist air at a temperature, at a humidity ratio, and at a total pressure. And it goes through and it interacts with a cooling fluid. Now, this particular case, it could be a refrigerant of some kind that is going through the evaporation process, and so its temperature is low enough to cause some of the vapor in the dry air mixture to condense. And as it condenses, it's picked up and it's taken away. Okay, and so that's the first process. And so as we get through this particular process, we see that the humidity ratio decreased, the temperature decreases, we take away just enough, in this particular case, we take away just enough moisture such that the relative humidity, which came in at a certain condition, drops or goes to the saturation condition. Okay, so we'll take a look at that, where that is on the cyc chart in just a second here. And so if we were to plot the location of state 1, here is the temperature 1 at a given humidity ratio. We could actually determine the value of the relative humidity. And so that's our initial state right here. The process of cooling down and losing moisture is moving in this direction as we cool down, as the dry bulb temperature decreases, but more importantly, as the humidity ratio drops because some of that moisture is leaving the dry air mixture. And so as much moisture as necessary is brought out such that we reach the saturation condition at a lower temperature T2. And so that's the location of this mixture here. And then in order to send that lower humidity air out, that lower amount of humidity ratio out into the room, we run it through a heating coil, and at constant humidity ratio, because we're not adding any additional vapor, we heat up the dry air and the moisture to a more convenient temperature T3. And so this would be our final condition after going through the humidification process. We have to bring it down to a low enough temperature in order for the vapor to condense, but then it's actually too cold and we actually have to bring it back up in temperature and drop the relative humidity. And so in this region, this would be more comfortable to the person that is receiving that cool, drier airstream. And so if we look at the equation, this particular problem asked to determine what would be the mass flow rate of the refrigerant when compared to the mass flow rate of the dry air. So it's this stream versus this stream here. And so the mass flow rate of the refrigerant is coming in at I and leaving at E, and they have enthalpy values associated with them. So the refrigerant is going through, let's say, the evaporation process, and so this m dot r times this enthalpy rise is that heat transfer. And that heat transfer is going to be equal to the heat transfer that is taken from the moist air. And that's going to be the m dot a times this numerator here. And so this numerator is similar to what we saw before. It's this value right here for the Q dot CV. We have the air component, we have the water removal component, and we have the moisture component. And so we come back here, we see the air component, we see in this case here, we see what's happening to the vapor that's in the airstream, and then we see this term right here times the m dot a is the water removal rate times its value of enthalpy. And so this would be the solution to how much refrigerant flow rate do you need to actually perform this dehumidification. And again, what it looks like on the psychometric chart. Keep in mind, if this was a psychometric chart with all the scales, there would be a line, an axis that would correspond to the humidity, the enthalpy at a given condition. And so one could actually come up and grab this humidity value for this state, and it turns out that the humidity value for this state right here would actually be equal to this term in addition to this term. The humidity value, or the enthalpy value for this term right here, if I were to pick that up, would actually be equal to this value and this value together. And so the psych chart allows you not to have to look at the two components separately, but the two components together as a difference in the mixture enthalpy with respect to the mass of dry air. If we want to do the reverse of that, if we want to add moisture to the air, we could come in with a moist air mixture at a temperature and at a humidity ratio value, and we could inject water. Now we could either inject liquid water or higher temperature vapor water. Okay, so this could be just going across a mat that is saturated with liquid water, and as the air flows through, it picks up the liquid. It actually causes the liquid to vaporize and enter into the mixture. Or it could be steam of some kind. We could actually be injecting high pressure, high temperature steam and allowing that to add to the moist air, both in terms of its temperature as well as its humidity ratio. And so in the case where we are adding steam or vapor, we would have this as our psychometric chart. We start at this point at a low dry bulb temperature at a low humidity ratio, and the effect of adding the higher temperature vapor causes the mixture not only to rise in temperature, but to increase in humidity ratio. And so the process for injecting vapor would look like this, going up in that direction. Likewise, if we had, let's say we had warmer dry air at state 1. So we're coming in relatively warm with a low value of moisture. And if we allow water, liquid water, to evaporate and join the mixture, that evaporation process takes energy out of the dry air and causes the dry air to cool. And so our final state would be here at a lower dry bulb and at a higher value of omega. So this process, which actually cools the dry air at the same time, adds humidity. Okay, this particular process where you start off with relatively warm, very dry air, where we just allow moisture to come in through a some type of a wetted mesh, is what's called a swamp cooler. And so you could actually air condition or cool the air in a desert, let's say, by just allowing very warm, very dry air to pass through water, a water bath of some kind, a saturated cloth of some kind, and that would actually cool the water as well as it raises the humidity level, but it's not an uncomfortable amount of humidity. This process here obviously would allow moisture to come in, but at the same time it also increases the temperature. So this would be possibly a process where you want to try to take cold or cooler dry air in the winter time and bring it up both in temperature and to a humidity value that is more comfortable. So that's the humidification process. And so what I just mentioned over on this side here is called evaporative cooling. And as we see here, we bring in relatively warm, dry air through a gauze, a soaked pad that has water, and that basically the hot air causes energy to cause the water to evaporate and join the mixture as a higher value of omega, and at the same time increases the temperature. And what this is actually showing you that process starting at 1, which is relatively high temperature, low value of moisture, and having it decrease the temperature to state 2. And in this particular problem, as they show the mixture enthalpy scale going from state 1 to state 2, going up and picking up a value and picking up a value, the first law equation, as you can see here, they've separated the components a little bit such that this term right here, which is the dry air enthalpy, in addition to the moistures, the moisture enthalpy, this term right here is actually at state 1, it corresponds to this mixture enthalpy term. Likewise, this term right here, which is the dry air at the second state and the moisture at the second state, this combination term here is actually the mixture enthalpy at this point. And then what you have as part of this energy balance, since you had water coming in at a given temperature, it has a liquid enthalpy associated with it. And this change in omega is really how much water was put in. How much water was put in. It's the difference in the omega. So this is a positive influence, and so this is enthalpy that's added to this enthalpy. So it's this point, and then the difference would be this, and that would then be equal to this term here. What is missing in this equation, this first law equation, is just the m dot a. And so that m dot a we saw before when we wrote this equation here was in each of the terms. And so all that was done is that this bracketed term here has been set equal to each other. And the combination of these two terms is actually pulled off of the psychometric chart. One of the final things that we can also look at is the adiabatic mixing of two moist streams. And this happens a lot in air conditioning processes where we bring in, maybe we bring in outside air that has a temperature and a humidity ratio associated with it. Then we bring in air from a room, and we mix the two together to form a third state. And so in a situation like this, we have two streams. Each stream is characterized by an m dot dry air. Each stream has its own temperature, and each stream has a humidity ratio associated with it. And if we assume the mixing process occurs without any work and fully adiabatic, our final output condition would obviously, from a mass balance, would be the mass of dry air at this state is just the addition of the two. The humidity ratio is going to be directly related to the two humidity ratios. Again, adding the two moisture components and dividing it by the total mixture of dry air. And then the temperature that comes out would be a direct result of the first law of thermodynamics. And so again, this is a very common process that's associated with air conditioning. The final condition is a cooling tower. And what we see here in this cooling tower is that atmospheric air is brought in, is inducted in, and is forced or is caused to then exit because of a fan. And we then have water that is coming from a condenser. And so this is part of the condenser of a vapor power plant. And this is warm feed water. And so this warm feed water at a temperature T1 is allowed to be sprayed in, and that warm water then is entrained. Some of that warm water is entrained by the atmospheric air. The air accepts it, and at the same time, the remaining warm water is actually cooled down. And it's because the warm water coming in here gives up some energy to cause some of it to evaporate and be entrained by the atmospheric air. And when it gives it up, the rest of the warm feed water cools down. So it is a way that we can go from warm feed water to a cooler feed water. We lose some water in the process, but we have to make up some water, and so we can talk about the temperature going down and the rate of water has dropped some. But if we balance these two water flow rates by putting in some makeup water, we then have a way to cool this warm feed water. And it's cooled because this air has a humidity ratio that can still accept some vapor, and it fully saturates usually. So the discharged moist air is discharged with a higher value of humidity ratio and typically a higher temperature. But the mass of dry air, as you see here, stays the same. And so it's very similar to the process that we saw before, where we brought in a mixture of moist air and come out with a mixture of moist air by injecting liquid water. And so it would be similar to kind of what we did, in one of these processes here. We come in, we inject some water. That injected water actually cools some of the water, and the other part of the water drops out into some basin here. Okay, so we'll take a look at some example problems. We'll go into the test software to see what problems we can do and what new test app that we've not seen will allow us to determine the properties on a psychometric chart. We finish up this chapter with just the key equations associated with the ideal gas mixtures, the psychometric applications, the definitions of the humidity ratio that we've been talking all about, the humidity, the relative humidity value that we've been talking about, and the mixture enthalpy that is on the psychometric charts.